All right, let me see here. Okay, you guys out there in Zoom, can you hear me?
Yes, sir.
Okay, good. All right, let me start by taking roll. Today is the 24th. Okay, so Anderson is here. Chesmore. Gonzalez is here.
Here.
Hickey,
Here.
Islop, Jabbar, Jones, Labrador, oh. McKeon,
Here.
Miller,
Here.
Peterson,
Here.
Papa, Simpson, and Welter. All right. Okay, so we're going to continue our discussion of kinetics. Oh, and by the way, before I forget, so I don't know if you have noticed, but I have added 2 more questions to assignment 2. Remember, I said that there were some missing question dealing with rate laws. All right, so I added 2 more questions. So if you go back to the link in Canvas, you'll see that the very last 2 questions are 2 questions of the type that we looked at last time when we were doing rate law problems. So if I remember correct, we did do this one. I remember this one. Now, what I want to remember also, did I do this one in class last time? Yes, no, maybe so? No? Okay. Let me go through this one quickly. It's pretty much the same idea as the previous example. You're given the data where you're given the concentrations and various concentrations of the reactants and their corresponding rates over here. Where is the stylus? Okay, so pretty much the same idea as before. So first thing I'm going to do is write a general rate law. Let me do it over here. Rate. Okay. Rate is equal to the rate constant K times the concentration of S2O8 minus, if I remember correctly, that's called the persulfate ion, raised to the X power, multiplied by the concentration of I minus, raised to the Y power, all right? Okay, so let me see if you remember what we did the last time. I'm going to start you off by writing this down, right? So what do you think the next step is? Anybody? If you remember what we did the last time, you can refer to it in your notes if you have it. Okay, so what would be the equation for experiment 1? The rate, which is equal to what? 2.2 times 10 to the minus 4 m over s is equal to what? K times 0.08 m raised to the x multiplied by 0.034 m raised to the y. Okay, very good. So this is for equation 1 or experiment 1, and we do something similar for experiment 2. So for experiment 2, it would be what? Okay, 10 to the minus 4 m over s, and that is equal to k times 0.00, I'm sorry, 0.088 m x times 0.017 m raised to the y. And then, as you said, You divide the top by the bottom. Oh Lord, I can't even draw a straight line on this thing. Okay, and some things will cancel out. The units will cancel out, and the K's will cancel out. The 0.08 will cancel out. These units will cancel out. So you'll be, oh, and 10 to the minus 4 will cancel out here and here. So you'll be left with 2.2 over 1.1 equals to 0.034 divided by 0.017. And you'll see that this, oh, and this should be raised to the y, by the way. And this part here will work out to be equal to 2. And this part here will work out to be equal to 2 raised to the y, which means that y is equal to 1. Right? So the order of the reaction with respect to the persulfate would be 1. All right? So that's for X. Now we have to do the same thing for Y. So how would you recommend that we do that? Well, let me ask you, are you finished with this part here? Can I erase this part here? Going once? Going twice? All right, let me start erasing. Okay, so what next? This time we need to find Y, right? So turn on pen function. So what's the next step? I wouldn't do that. You know why? Can anybody tell me the reason why you wouldn't do the equations for 1 and 3 and then divide one by the other? Because what's that? Well, in order for you to do that type of thing, the concentrations of one of the reactants must be held constant. You see what I'm saying? That's the reason why we could do 1 and 2, because in both cases, the concentration doesn't change between 1 and 2. So you have to choose 2 and 3, exactly, because in the case of 2 and 3, these two don't change. So any change in the rate will be due to the change in the concentration of the persulfate. So for experiment 2, what would be the equation you'd write down when you plug the numbers into this equation right here? For equation 2. 1.1 times 10 to the minus 4 m over s is equal to what? K times 0.08 m raised to the x times 0.017 m raised to the y. And then for equation or experiment 3, what do we write down? This should be minus, by the way. 2.2 times 10 to the minus 4 m over s is equal to k times, ooh, what did I do? Okay, so k multiplied by what? Point 0.16 m raised to the x multiplied by 0.017 m raised to the y. Okay, so again, some things will cancel out. The 10 to the minus 4 here and here will cancel out. The units here will cancel out. The k's will cancel out. The m's will cancel out here. And these, all of this here will cancel out with all of that. So you'll be left with 1.1 divided by 2.2 equals to 0.08 divided by 0.16. And all of this will be raised to the exponent. So the 1.1 divided by 2.2 will give you 0.5. The 0.08 divided by 0.16 will give you 0.5 raised to the x, which means that again, x will be equal to 1. So therefore, the rate law will be equal to K times the concentration of the persulfate, 8, 2 minus, multiplied by the concentration of iodide. So that would be the rate law, all right? Which answers the first part of the question. The second part says you're to calculate the rate constant. Remember, the rate constant is K. And I think we did that as well in the previous example. So how would you solve for K based on the rate law and the data that's given? Okay, so K will be equal to rate divided by concentration of S2O8 2 minus times the concentration of I minus. And then what? After that rearrangement, what's the next step?
You choose one of the experiments and put them back.
Okay, so I always choose the first one. So let me do that now. 2.2 times 10 to the minus 4. And M over S will be the units here. Divided by 0.08 M times 0.034 M. And we work that out. Okay, let's see what this gives. So 2.2 times 10 to the minus 4 divided by 0.08 divided by 0.034. And this must be rounded off to 1 sig fig basically. So according to my calculations, this works out to be 8 times 10 to the minus 2. And as far as the units are concerned, this M will cancel out with that M. So you'll be ending up with M to the minus 1, S to the minus 1. So this would be the rate constant. All right? Any questions? Any questions about this particular example? So as I said before, I added 2 questions of this type. Basically, it's the same thing. You take the same approach to solve those problems. All right? So make sure you do those questions. All right. Okay. Is it okay for me to move on to the next slide? All right. So what we're going to do now is talk about some specific types of reactions where the concentration order of the reactants will be 0, 1, and 2, right? That's what we have been concentrating on all along. But this time, what we'll be concerned with is determining an expression for the relationship between the concentration of the reactants and time. The rate laws that we discussed earlier, like the problem that we just looked at, we were concerned with the rate law expressed as the rate is equal to rate constant multiplied by the concentration of the reactants raised to certain power. So in other words, we were concerned about the relationship between rate and concentration. Now we're going to look at the relationship between concentration and time for 0-order reactions, 1st-order reactions, and 2nd-order reactions, all right? So in the case of 0-order reactions, we're assuming that we have reactant A, and it forms, its products, all right? So we can write down a rate expression, which would, of course, be measured in terms of the rate of disappearance of A, given by this expression right here. And we can set that to be equal to K times the concentration of A raised to the 0, right? So that means that a reaction is 0 order with respect to A. And as we all know from your previous math experience, anything that is raised to the 0 is equal to 1. So therefore, this simplifies to rate is equal to K. So what does that tell us? It tells us that the reaction rate is not dependent on the concentration of the reactant. And believe it or not, there are some reactions that are like that. It doesn't matter if you increase or decrease the concentration, the rate remains the same, a constant value, all right? So we can rearrange the equation here to solve for K, the rate constant, and the units for K in this case would be the unit of rate, basically. And it depends on what unit you use for measuring the rate, in particular, the time unit, all right? So that's that. Now, based on that, we can set this equation here, or this expression, to be equal to K, and this is what we're going to end up with. And then we can do what they call in calculus integration, which I won't go into. If you need me to show you how to do that, I can show you if you come to my office hours. But basically, by integration and then some rearrangement, you're going to get this equation right here, right? And this equation here relates the concentration of the reactant at a particular time, right? So just to define the terms of this equation, A is the concentration of the reactant, or this here is the concentration of the reactant A at any time. This here, concentration of A0, is the concentration of A at the origin at time equals 0. And of course, K is the rate constant and T is the time, all right? Now, at this juncture, I want to introduce to you this term, which will become important not only in this chapter, but later on in the chapter of nuclear chemistry, and it's called the half-life, right? And here's a definition of the half-life right here. The half-life is the time required for the concentration of a reactant to decrease to half its initial concentration, right? So in other words, when the time is equal to the half-life, the concentration of the reactant at that time would be equal to the initial concentration of A divided by 2, all right? So if we put T half here, where T is, and concentration of A initial over 2, where we have A here, you're going to end up with this equation. In fact, let me show you how that is done. So I skipped a few steps, so I'm going to show you those steps going from here to here, given this right here, all right? So basically, let me see if I can squeeze it in here. So if T is equal to T half and concentration of A is equal to initial concentration of A divided by 2, then this is what you're going to end up with, right? That will be equal to initial concentration of A minus K T half, all right? And then now what we can do is we can add K T half to both sides and subtract A initial over 2 from both sides. And you're going to end up with K T half is equal to the initial concentration of A minus the initial concentration of A over 2, which works out to be equal to initial concentration of A over 2, right? And therefore, T half would be equal to initial concentration of A over 2K, which is this equation right here, all right? So in the case of a zero order reaction, if you want to calculate the half-life, remember what the definition of the half-life is. It's a time taken for half of the amount of reactant to react. Then basically this is the equation you're going to use. You're going to need to know what the initial concentration is, and you're also going to need to know what the rate constant is in order for you to calculate the half-life of a zero order reaction. And one interesting thing about this equation here is that if you look at it closely, you see that this equation is in the form of Y is equal to C minus MX, right? So basically it's of the type of equation which represents a straight line plot where the slope is negative. So if you plot A versus time, this is a graph you're going to get. This is the plot where the slope is equal to minus K, all right? And as far as the intercept on the y-axis is concerned, that is when T is equal to 0. So if you imagine T equals 0 here, that means that A would be equal to the initial concentration of A, which would be right here. So that's basically the plot of concentration of A versus time for a zero order reaction, all right? Okay, any questions about this? Any questions? Any questions? I think there is an example or a question from the assignment. Let me see if I can bring it up. here. Assignments. Number 2, download. Okay, so let me see if, okay, no, that's not it. We did that one already. Okay, here we go. This reaction is a zero order reaction that the question is all about. And it says that the initial concentration of the reactant is 0.545 m, and it gives you the half-life. And then the question says, how much time is required to reduce the initial concentration of the reactant by 65%? And I'm sorry. For you guys out there in Zoom, I'm sorry, I forgot to turn on the share screen. So let me do that now. I apologize. I'm so sorry. Okay. So if you need any help with what I discussed before, please call me on Skype or see me in my office hours. And I'm more than willing to review what you may have missed. Okay, so all right. I don't know how to get rid of that. All right, so remember now, the equation that we just derived for the zero order reaction is the concentration of A is equal to the initial concentration of A minus KT, all right? Now the question gives us the initial concentration of A and the time, and it gives us the half-life. The half-life is 236 seconds. So this is the half-life here. This is the initial concentration of A, all right? Okay, so the question is asking, how much time is required to reduce the initial concentration of the reactant by 65.5%, okay? So the first thing we need to do is rearrange this equation here to get the time, which is what the question is asking for. So therefore, based on this equation, we can say that time would be equal to the initial concentration of A minus A over K, all right? So basically what we have to do now is put the numbers in. So we know what the initial concentration of A is, that's this right here. Now the concentration of A would be the concentration at time t, right? Which is what we're trying to find. We're trying to find t. The question says that the initial concentration was reduced to 65.5%, which means that the percentage of A remaining would be, 100% minus 65.5%, right? So that would be equal to what? 100 minus 65.5. So that'll be 34.5%. All right? So that means that the concentration of A would be 34.5% times the initial concentration. 34 times the initial concentration. So 34.5% multiplied by the initial concentration, which is 0.545 m. What does that give? Okay, so according to my calculations, and please do the calculations along with me because I could be making errors along the way. So just to keep me on my toes, make sure that you confirm what I calculated. Okay, so we have the concentration of A, which will go here. Now, the only thing that's left for us to do is to determine what K is. Now, the key to determining K is the half-life right here. And if you recall, we said that the half-life for a zero order reaction would be the initial concentration of A divided by 2K, right? So therefore, we can say that K will be equal to the initial concentration of A divided by 2 times the half-life. All right? So let me show what that gives. So the initial concentration is 0.545 m divided by 2 times the half-life, which is 236 seconds. And that would be equal to 0.545 divided by 2 times 2, 36. Okay, so according to my calculations, the K for this problem is rounded out to 3 sig figs would be 1.15 times 10 to the minus 3, and the units will be m over s. All right, so we have all the things now we need to calculate T. We have the initial concentration, which is 0.545 m, minus the concentration at time T, which is 0.188 m, divided by K, which is 1.15 times 10 to the minus 3 m over s. And let's see what that gives. So 0.545 minus 0.188. And then we divide that by 1.15 times 10 to the minus 3. And according to my calculations, rounded out to 3 sig figs, that would give 310 with a dot, right, a decimal point right there. And the units, of course, would be seconds. And that's how that would be done. All right. Any questions about this example? Okay, somebody has a question in the chat. Oh, somebody just said thank you. Okay, you're welcome. Ms. Jabbar. Okay, any questions about this? Any questions? Any questions about this particular example? Any questions? No questions? Okay, so can I delete this, all of this? All right, let me clear that. And let me go back to the PowerPoint. Well, let me get out of this first, then the PowerPoint. And let me go full screen with this. Okay, so we just covered this zero order reactions. So the next type of reaction we'll be looking at in this series are the first order reactions, right? So we're talking about the reactions where, again, you're going from your reactant A to the product. The rate will be equal to what we saw before in terms of the change in concentration of A versus change in time. Of course, it's negative because A is the reactant. It is being used up. So therefore, in terms of the rate law for this reaction, rate will be equal to K times the concentration of A raised to the first power, all right? So that would be the rate law for a first order reaction, all right? So we can rearrange this to get K is equal to rate divided by concentration of A. And the units of K in this case would be the rate units, M over S, divided by M, which is the molarity unit or concentration unit. And this works out to be 1 over S or S to the minus 1. So basically, the units of rate constant for first order reaction would be some unit, would be 1 divided by some unit of time. So it could be seconds, it could be minutes, it all depends on how fast or how slow the reaction goes, all right? Now, the next thing I want to talk about is how do we derive the equation representing the relationship between the concentration and time for first order reaction, right? So again, what we do is set this expression to be equal to this time Ka, and again, some calculus is involved, which I won't get into again. You have to do some calculus, which involves a couple of steps. But the final result is that the relationship between the concentration of the reactant and time is given by this equation here. The concentration of A is equal to the initial concentration of A times e to the minus kT. Now, I don't know if you're familiar with the E constant, right? It's a function on your calculator. If I remember correctly, it's equal to, in fact, I can find out what it is. E, I know it's 2 point something. 2.718 and some other digits, all right? It's a constant, all right? So basically, this is the relationship between the concentration of A at time T, the initial concentration of A times E raised to the minus KT, right? And if you were to plot concentration of A versus T, this is what you're going to get. And one important and interesting feature of this equation, or I should say this plot, is that this curve here, this part here, as time progresses, will approach the x-axis but doesn't touch it, right? And I'm quite sure you probably met some interesting graphs in math where that is the case, right? It comes close to the x-axis but doesn't cut it at all right? Okay, now when it comes to these things, we like straight line graphs because you can get more information directly from the slopes and the y-intercept especially. So what if you rearrange this a certain way, you're going to get this. Now, how do you do that? Again, this is something that you should know from your math course. In fact, let me see if I can show you. Let me see if I can squeeze it here. So basically what you do is find a natural log of both sides. So you're going to get natural log of A, concentration of A, will be equal to the natural log of the initial concentration of A, plus the natural log of E to the minus KT, right? Now, as far as this is concerned, this can be expressed as minus KT ln E. And this would be still ln initial concentration of A, and this would be ln the concentration of A, all right? Now, as far as ln E is concerned, can anybody tell what that is equal to? Yes, sir.
1.
1, exactly, right? The natural log of E is always 1, just like the what do you call it, log to the base 10. Log to the base 10 of 10 is 1 again, right? So basically, this simplifies to this right here, right? If this is 1, then you're going to end up with ln A is equal to ln the initial concentration of A minus KT, which is what you have here. And if you look at this equation carefully, you'll see that this equation is in the form of Y is equal to C minus MX, right? So Y would be the plot of the ln A, C would be the y-intercept, and the slope would be given by minus M or minus K, all right? And T, of course, is a plot on the Y on the x-axis. So if you plot this graph, it's going to look something like this, where the slope would be equal to minus K, and the intercept on the y-axis would be the natural log of the initial concentration of A, all right? So those are all the consequences of the first order reaction. Now, one more thing I want to talk about, and this goes back to the half-life definition that I introduced to you with respect to zero order reactions. This can also be applied to first order reactions and second order reactions, as you're going to see here. But what you're going to see is that to calculate it, the equation will be different. So just to remind you, the half-life of a reaction is the time taken for half the amount of the initial substance to react, all right? So applying that to the equation that we just derived, right? We again replace T with T half, which is a half-life, and replace A with the initial concentration of A divided by 2. So basically, and I think I need to remind you of what we're talking about here. The equation that I exposed you to before is, I'm trying to remember the form. It's ln concentration of A over concentration of A initial is equal to minus KT, all right? Minus KT. Let me use black ink instead. Okay, so minus KT, all right, that's the equation. And by the way, and you should recognize this equation is the same thing as ln concentration of A minus ln the initial concentration of A equals to KT, all right? So these are just two different ways of saying the same thing. In any case, what we have done to get this expression is and let me just point this down here, we replace A with half of initial concentration of A, so that becomes ln Okay, what am I doing? Okay, ln concentration of A, initial divided by 2, divided by initial concentration of A. And that would be equal to KT half. And then to get the half-life expression, let me just put it here, T half would be equal to ln the initial, oh, by the way, this should be minus, very important, can't forget the minus sign. So this would be equal to ln initial concentration of A over the initial concentration of A divided by 2 minus divided by K. And actually it's the other way around. This should be divided by 2. I keep messing up. Sorry about that. Let me take this out. That's what I meant to put. Okay, and let me just extend this line here. And divide by K, all right? So the half-life will be equal to minus ln the initial concentration of A divided by 2 divided by the initial concentration of A. And if you examine this equation, you see that these two equations are saying the same thing, all right? Because if you remove the minus sign, you have to switch the numerator and denominator for this part right here, and that would be equal to this part right here, all right? So in any case, continuing, the initial concentration of A will cancel out, and this simplifies the ln 2 over K, all right? Same thing would happen if you use this equation here. This would be equal to minus ln half over K, which would be the same thing as ln 2 over K, all right? So basically what this is saying is that the half-life for a first order reaction is equal to ln 2 divided by K. And if you put ln 2 in your calculator and press the equal sign or execute sign, you're going to get 0.693 and some other digits. So sometimes you'll see just 0.693 indicated in some textbooks and so on, all right? So that's the equation for the half-life of a first order reaction. Now, one interesting point that I want to make about this equation is that if you look at this particular equation, the half-life is equal to ln 2 divided by K, you'll see that there are no concentration terms. You don't see any concentration terms in that equation. And what that tells us is that for first order reaction, the half-life is constant, as long as the K is constant, right? Which it is at a constant temperature, all right? So that's one big difference between the first order reaction and the zero order reaction that we saw before. In the case of the zero order reaction, the half-life has a part of it, the concentration of A initial in that equation. So therefore, in that case, the half-life is dependent on the initial concentration of A. In this case, the half-life is independent of the concentration of A. It is only dependent really on K, right? And K is a constant at constant temperature. So therefore, the half-life is constant for a first order reaction, all right? So here is a question based on what we just looked at. It says, what is the half-life of N2O5 if it decomposes with a rate constant of 5.7 times 10 to the minus 4 seconds to the minus 1? Now, one of the things that you have to pay attention to when doing these questions is that you have to ask yourself, well, what type of reaction is it? Because the question didn't directly give you whether or not it's a first, second, or a third order, all right? Or I should say, sorry, zero first or second order, all right? The question doesn't explicitly say that, but you can tell what order it is. Why? Because of the units, right? The unit of half-life for a first order reaction would be some unit of time raised to the minus 1, right? And that's because, again, it's based on this equation right here. Half-life is equal to ln 2 over K. So therefore, if the half-life unit is in seconds, then the unit of K must be seconds to the minus 1. All right? So therefore, based on that, you know that the order of the reaction with respect to N2O5 would be 1, would be a first order reaction. So basically, all we have to do is plug the numbers into this equation that we just derived. Half-life, in fact, I think I have a solution. I don't think I need to write anything here. Hold on. Let me just erase this just to make sure. So, right, here we go. So this is the half-life equation for the first order reaction. All we have to do is plug in the K value, since they gave you the rate constant, and then do your thing on your calculator. And according to this, the answer should be 1200 seconds, which is approximately, well, not approximately, 20 minutes, all right? And that's it. That's how that question is done, all right? Any questions about this? Any questions? Any questions? Oh, and we just dealt with this. How do you know the decomposition is first order? Because of what I said. The units of the half-life is seconds to the -1, which means that it must be first order based on the half-life equation for first order reactions. Okay, so let's look at this particular plot. And I think this is dealing with the same reaction here. And as I said before, let me go back to the previous, not this slide, but the one before this. Remember I said that for a first order reaction, if you plot the natural log of the concentration on the y-axis versus time on the x-axis, you're going to get a negative slope where the slope would be equal to minus k, and the intercept would be equal to the natural log of a initial, the concentration of the reactant initial. So this is directly applicable to this reaction, which is a first order reaction, right? The decomposition of N2O5. So somebody did this experiment and got the data and did the plot, and this is what they ended up with. And again, you can see it's a straight line where you plot the natural log of N2O5 versus the time, and based on the slope, you can find out what the rate constant is. And we all know how to determine the slope, the rise over run, right? And you find so in this particular case, the rise would be a negative rise because you'd have to do 20.34 minus 21.5. So that would be the rise, and the run would be 2430 minus the 400, and you divide the change in y over change in x, and that would give you the slope of the graph, which gives you the minus rate constant. And then the intercept, of course, would give you right here, would be the natural log of the initial concentration of A. And based on that, you can find out what the actual initial concentration of A is, all right? Okay, so that's basically dealing with the first order reaction. So this is another example. Let's look at this one. It says, it gives you the reaction, and it says it's first order. So they explicitly tells you it's first order, and it gives you the rate constant. And the question is asking, how long will it take for A to decrease from 0.88 m to 0.14 m? So in this question, they gave you the rate constant K, they gave you the initial concentration of A, and they gave you the concentration of A at the time that they're asking for, right? So basically, the question is asking for T, all right, the time. So this is the equation we can use, and we have everything we need. They gave you the constant, they gave you the initial concentration and the concentration at time T. So it's all a matter of rearranging it to solve for T. So T will be equal to ln A initial minus ln A over K, which is the same thing as this, right? And then you just plug the numbers in. All right, 0.88 divided by 0.14. Find the natural log of that, and then divide it by the rate constant K, which is 2.8 times 10 to the minus 2. And then do your number crunching. And according to this, the answer should be 66 seconds. All right. Any questions about this one? Any questions? Any questions? All right. So, in the case of a first order reaction, as we said before, the half-life is constant. The half-life doesn't change. As long as the temperature is constant, the half-life is constant. And that is demonstrated in this graph right here. So basically, you start off with A initial right here, and then one half-life passes by. So the concentration falls from A initial to half that amount, right? And then after that, another half-life passes by. So this is halved again. And then another half-life passes by, and that's halved again, and that just continues, all right? So after first half-life, the concentration of A would be equal to the initial concentration of A divided by 2. After the second half-life, the concentration of A would be equal to the initial concentration of A divided by 4, and so on and so forth, right? So basically, at each time after half-life has lapsed, the concentration will be reduced from half to what it was before, a half-life away, let's put it that way, all right? So that's basically what is observed in a first-order reaction. The half-life is constant. And again, remember, the half-life in the case of a first-order reaction is constant because it's not dependent on any concentration terms. In the case of a zero-order reaction, it was dependent on the initial concentration of A. So for that reason, the half-life is not constant in the case of the zero-order reaction, but it is constant in the case of a first-order reaction. Okay, so now we're going to move on to second-order reactions, all right? So in the case of second-order reactions, again, we have A reacting to form a product, and of course, the rate, again, will be equal to negative the change in concentration of A with time, and rate for the rate law, I should say, for a second-order reaction is equal to K times the concentration of A raised to the second power, right? So what we can do, firstly, we're going to find out about the units. What would be the units of K in this case? So we rearrange this equation. Let me go back to my pointer. We arrange this equation here to solve for K, and this is what we end up with. Rate, excuse me, rate is equal to K. K is equal to rate divided by the concentration of A squared, all right? So if the rate units is in ms or m over s, and the concentration of A squared units will be m squared, then this simplifies to 1 over m times s, right? And again, s can be the unit, but of course it can be replaced by any other unit of time, again, depending on the reaction, how fast or slow it goes. So the time unit could be minutes, hours, whatever, days, years, whatever, all right? So that's how you determine the units of K in the case of a second order reaction. So what we're going to do is something similar to what we did in the previous two examples for zero and first order reactions. We're going to set this here to be equal to this. And again, I'm going to jump some steps because some calculus is involved. Basically, after going through those steps, this is the equation that we end up with, which relates the concentration of A to the time, right? So in this particular case, the equation is 1 over the concentration of A is equal to 1 over the initial concentration of A plus K, which is a rate constant, multiplied by time, all right? So this is just reminding you of what the different terms are. So now we can calculate the half-life for a second order reaction. So when T half is equal to T, the concentration of A is equal to the initial concentration divided by 2. So we put T half here, and we put A initial over 2, where A is right here. And we end up with this equation. I won't go through the steps. If you need help with that, let me know. You can come and see me or call me on Skype, right? But basically, when you substitute T for T half and initial concentration of A divided by 2 for A here, then you're going to end up with this equation right here, right? So this equation here gives you the half-life of a second order reaction. And again, as in the case of the zero order reaction, the half-life is equal to, well, it's dependent on the initial concentration of A, right? So the first order reaction is unique in this sense, in the sense that in the case of the first order reaction, the half-life is not dependent on any variable whatsoever. But in the case of the zero order and the second order reaction, the half-life is dependent on the initial concentration of A. So again, we can do a straight line plot, recognizing that this here, 1 over A would be the Y, and 1 over initial concentration of A would be the C, K would be the M, and T would be plotted on the x-axis. So if you plot 1 over A versus T, you're gonna get this plot right here, where it's going to be a straight line, where the slope will be equal to the K, the M, be equal to the K, and the intercept on the y-axis is going to be equal to 1 over the initial concentration of A, all right? So that's basically the result of the second order reaction, all right? Okay, so to summarize, for the zero order reaction, that was the first one we looked at, the rate law would be rate is equal to K. Remember, the concentration of A is raised to the 0 power, so that equals to 1. So the rate is equal to K. The equation relating the concentration to time is this equation right here. We derived that. And the half-life equation is this right here. All right. In the case of the first order reaction, the rate is equal to K times the concentration of A. The equation which relates the concentration of A to time is given by this, and there are other ways of expressing it, but this is the linear form, all right? This is the one that you can plot a graph based on this equation. And the half-life equation, as you recall, is ln2 over K. And then finally, in the case of the second order reaction, the rate is equal to K times concentration of A squared. The equation relating concentration to time is what we just derived here. And the half-life equation is 1 over K times the initial concentration of A. So that's a summary of all those equations applicable to zero, first, and second order reactions. All right. Okay. What time is it? 8:53. Okay. Let's go to the assignment again. And let's see what comes up next in terms of questions. Oh, guess what? I did not finish question number 4. How about that? Okay. So let me continue with question number 4, the B part. It says how much reactant remains after 6.78 minutes. All right. Now the equation that we would use, now remember, this is a zero order reaction. So the equation that we would use in this case, let me get my pen thing working here. Okay, so the equation that we would use, let me write it here, is concentration of A is equal to concentration of A initial minus KT. So that's for the zero order reaction. The question is asking for A, how much reactant remains after 6.78 minutes? The initial concentration was given earlier. What was it? Can somebody tell me? I don't want to scroll up because I have to go through a lot of. What was the initial concentration from the A part? Can anybody? 0.545 M. And what was the K? We calculated K, right? M over S, right? Yeah. And the question gives us time, right? So let's see if we can solve this. The concentration of A is equal to 0.545 M minus K, which is 1.15 times 10 to the minus 3 times the time, which is, oh, don't forget the units, would be M over S multiplied by the time. The time is 6.78 minutes. But guess what? We have seconds here. So what we need to do is convert the minutes to seconds. So we're going to put 1 minute down here, 60 seconds above, and then we do the math. So let me do that right now. 1.15 times 10 to the minus 3 times 6.78 times 60. And then I'm going to subtract that from 0.545. What did I do wrong? 1.5. Okay, so according to my calculations, this works out to be equal to 0.077 M. All right? And that's how that is done. Okay. Any questions about this? Any questions? Any questions? Okay, we're going to ignore this one right here. So leave that one out, because that was
We're not doing.
exactly. It's kind of impossible to calculate how much reactant will remain after 4 half-lives for a zero order reaction. We can do that for a first order reaction, but not for a zero order reaction. All right, let me see here. Can I clear this? All right. And let me see if there's any more parts to this question right here. Okay, very interesting question here. At what time will the reaction be over? So let me rewrite the equation that we're going to need again. Same equation as before. It is concentration of A is equal to concentration of A initial minus KT. So how would you solve this problem? The question says, at what time will the reaction be over? So let me ask you this. What will happen if the reaction is over? No reactant left, right? So that means that when the reaction is over, the concentration of A would be 0, right? And that would be equal to concentration of A initial minus KT, right? So basically, all we have to do is solve for T. T would be equal to initial concentration of A divided by K, right? And the initial concentration, if I remember, was 0.545, right? And K was what again? 1.15 times 10 to the minus, was it 3? From the previous part?
Yeah.
10 to the minus 3 M over S. Whatever that gives, that would be the answer. So 0.545 divided by 1.15 times 10 to the minus 3. And according to my calculations, rounded off to 3 sig figs, the answer becomes 473, and the units will be seconds. All right. And
Since it's zero order, we can also just double that.
no.
No.
No. Because again, the half-life is not constant in the case of a zero order reaction.
That was constant. I thought it was not constant.
Hmm?
I thought it was not constant in the higher.
You thought it was non-constant what?
Like in the higher order reaction.
No, for zero and second order reaction, it's not constant. It's only constant for the first order reaction. Yeah. Okay, any other questions about this particular question in the assignment? Now, let me scroll down. Oh, shoot, I shouldn't have done that. Let me go back to this, clear this, close this, and then scroll down. Okay, now in this case, we're dealing with a first order reaction. And it's the same reaction that we looked at earlier, right? They gave us the rate constant at 25 degrees Celsius. And it says, what is the concentration of N2O5 remaining after 2 hours if the initial concentration is 0.50 M? So in this question, they gave us the rate constant. This is the rate constant here, K. This is T, 2 hours. And here they gave us the initial concentration of A. And the question is asking for the concentration of A at time T. So recall that the equation for the relationship between concentration and time for first order reaction is, well, one way of expressing it is concentration of A is equal to the initial concentration of A times e to the minus k, kt. KT, all right? So that's the equation we're going to use, and they gave us everything we need actually. So the concentration initial of A is 0.500 M multiplied by E to the minus k. Now, k is equal to 6.32 times 10 to the minus 4. And the units for this would be seconds to the minus 1. And that will be multiplied by 2.00 hours. But again, we have to do some conversion here because we have seconds to the minus 1 here. We have hours here. So we have to convert from hours to seconds. And 1 hour will contain 3,600 seconds. So the hour units will go, the second units will go, and that's this part right here. All right. So let's see what that would give. So that, according to my calculation, would give 3,600 multiplied by 2, multiplied by 6.32 times 10 to the minus 4. And then I put a minus sign in front of that. And then I put shift. Okay, and then I multiply by 0.5. So according to my calculations, and again, I'm willing to stand corrected, but this is what I got. I got 5.28 times 10 to the minus 3. M. All right, so that's what I got. All right. Any questions about this? Questions? Okay, so can I clear this? Thank you. Okay. So let me do that and scroll down. Okay. Now this question says, how long will it take, in other words, the time required for 90% of N2O5 to decompose? All right. So in this particular case, they're asking for T. Go back to this again. So the question is asking for T, right? Here's a key thing. It says 90% of the N2O5 decompose. So what that means is that the amount remaining would be 10%. So initially we had 0.5%, I'm sorry, 0.50 M. So therefore the concentration of A would be 10% or 0.1 multiplied by the initial concentration, which is 0.500, which would be equal to 0.0500 M, all right? So the question is asking for the time. Now remember, the equation we saw, where one form of the equation would be, let me write it here, Ln concentration of A over the initial concentration of A is equal to minus KT. What the question is asking for is T. So therefore, we can rearrange this to get T is equal to the natural log of A over the initial concentration of A divided by K. And don't forget the negative sign. I have a tendency to forget it. So we put the numbers in. That's minus Ln. The concentration of A is 0.0500 M divided by 0.500 M. And then we divide that by the K. What was the K? Can somebody tell me from earlier? I think it was given earlier in the question.
Not the question. No.
6.32.
That's it. Yeah, that sounds right. Minus 4. And the units is what? M over S, right? Oh.
Just that's.
Oh, just S, right. That's right too. Yeah. S to the minus 1. Okay, good. And that's it. So let's see what this gives. So 0.05 divided by 0.5, that gives you 0.1. And then you find the natural log of that. Take away the negative sign. And then divide that by 6.32 times 10 to the minus 4. And according to my calculation again, I have to run this off to 3 sig figs. So I got 3.64 times 10 to the 3, and the units would be seconds. And that's how that is done. All right. Any questions about this one? Any questions? Any questions? Okay, can I clear this? Going once, going twice. Okay. And let me do this. Let me scroll down here. Okay. So if you understood what we did in B, you should be able to understand what we do in C, right? Because in C, they're asking how long will it take for 90% to remain? So how would you deal with this one? It's the same equation. Let me write down the equation. T is equal to, oops, wrong thing. Write it here. T is equal to ln A over the initial concentration of A minus sign here divided by K. All right. So how would you apply that equation to solve for C? They said that 90% of the reactant remains. Well, we need to calculate the concentration of A. What would the concentration of A be? Because we know the initial concentration of A, what was it again? 0.545, right? The initial, right? No, I'm sorry, I'm thinking of another question. What was it? 0.500. Okay, 0.500. So that's the initial. So what would be the concentration of A at this time? Come on, folks, you should be able to answer that question. The question says 90% remains. So what's the concentration of A? If the initial was 0.500 M, then how do you get the concentration of A if 90% remains? Exactly. So that would be, and somebody's asking a question. Multiply, okay, so I think Ms. Jabbar is saying the same thing you're saying, Ms. Miller. Folks out there in Zoom, please feel free to chime in. Sometimes when I get carried away with doing these things, I don't pay attention to the chat. Okay, so as Ms. Miller just suggested, we multiply the 0.500 by the 90%, so that's tantamount to multiplying that by 0.9 times 0.500, and that will give you 0.450 M. All right. Then what? What do we do next? What do we do next? Right. So minus ln of 0.450 M divided by 0.500 M divided by K. What's K again? S to the minus 1, right? Okay. So let's see what that gives. 0.45 divided by 0.5. And then we find a natural log. And then we divide by, take out the minus sign. And then we divide by 6.32 times 10 to the minus 4. And according to my calculations, rounded off to 3 sig figs, the time it would take for 90% to remain would be 166 seconds. All right. Any questions about this one? Any questions? No questions? Okay, let me clear this. Do this, and in the 5 or 4 minutes we have left, we're going to look at D. And D is very easy. At least for me. So in the case of D, it's asking how long will it take for 50% remain? So what's the first thing that comes to your mind when you see 50% remain? You could do it that way and do like what we did in the previous two parts. But there's a much easier way to solve this problem. Half-life, right? Remember the definition of half-life? It's a time taken for half the amount of reactant to react. So half would remain, right? So what's the equation for the half-life of a first order reaction? Half-life is equal to what? ln 2 over K. And that's it. We know what K is. It's what? Remind me again, 6.32 times 10 to the minus 4, right? And this would be seconds to the minus 1. And that's it. So even though what Miss Miller suggested is correct, that's a longer way, right? Since we know what the half-life equation is, and we know it's 50% remaining, then that's all we have to do. So ln 2 divided by 6.32 times 10 to the minus 4. And according to my calculations, rounded out to 3 sig figs, that's going to be equal to 1.10 times 10 to the 3 seconds. All right. So that's basically how that is done. All right. I'm sorry?
Why is it?
Because of how we derive the equation. If I were to go back to, all right, let me just do this quickly. So the equation that we have for the first order reaction as it relates to the concentration relating to time is I'm trying to figure, okay, this form. ln A over A0 is equal to minus KT, right? So in the case of half-life, concentration of A would be equal to initial concentration of A over 2 divided by initial concentration of A. These two will cancel out. So you're going to get ln a half is equal to minus KT, right? So therefore, ln 2 is equal to KT, half. Don't forget that. You see that? And that's why this is so, all right? Okay, we're going to stop here for today. Let me check something here. Oh, shoot, why did I do that? Let me, here it is. Let me just check something about, okay. So based on what we have covered so far, I would want you to attempt question number 6. And that's it, question number 6, all right? You should be able to do question number 6 based on what we have done so far. Okay, let me see who came in late. I keep forgetting to catch those who did not come in on time. Is Hislop here? Hislop? Oh, okay. Jabbar is here. Jones is here. Papa, let me look here. Okay, Papa is not here. Simpson. Okay, I think I get everybody now. All right, so I'll see you guys on Monday.
The extra questions.
I'm sorry?
What's your extra questions you added?
Okay, yeah, I added to the original document and re-uploaded. So if you go there, it's the 2 last questions. So you should be able to do those 2 as well, all right? Okay, so let me, okay.